Okay, we're going to talk about some rules for integration. Now, the most powerful rule for integration, no pun intended, but I guess maybe a pun intended, is the power rule for integration. Now, there's two power rules. We're going to start with the simple power rule for integration. Basically, the simple power rule says that if we have x to the n dx, we can write that, where n is a power, we can write that as x to the n plus 1 over n plus 1 plus a constant. We got to remember the constant. As long as the n does not equal negative 1. N equal negative 1 is the only real number that this power rule doesn't work on. And we actually have a special rule for when n is negative 1. Now, let me show you why this works. Let me set it up for you, and I can easily show you why this works. Alright, so hopefully you can read my handwriting here. The derivative with respect to x of this result, x to the n plus 1 over n plus 1 plus a constant, if I checked it, remember the derivative of this should equal x to the n. And if this derivative of this equals x to the n, then this is the correct antiderivative. So first of all, how do we take the derivative of x to the n plus 1? Well, the derivative of x to the n plus 1, you can use the power rule for differentiation. Bring down the power, so that'd be n plus 1. Raise to the n plus 1 minus 1, reduce the power by 1. And then n plus 1 down here is just a constant. But notice that I have n plus 1 here and n plus 1 here, so they cancel. Now notice, remember, you can't cancel these if n was negative 1, because you'd have 0 over 0. So that's why n can't be negative 1. But otherwise, you can cancel n plus 1 over n plus 1 and get 1. And then when you subtract 1 from n plus 1, you just get x to the n. And then, of course, the derivative of the constant 0. So see, since the derivative of this expression right here is actually equal to x to the n, then I know I've got the right formula. Okay, now let's evaluate the indefinite integrals using this power rule. So we'll start out with a couple of simple ones. If you have x to the 5th dx, and you want to integrate that, then using this power rule, that would be x to the 5 plus 1, and then you just divide by the new exponent, 5 plus 1. So that would simply be x to the 6th over 6, and then you add the constant. And of course, you got to make sure you add the constant on indefinite integration. So now, this one's a little bit more difficult, but not too bad. T to the 1/2 dt, if I want to integrate that, then I add 1 to a half, and that gives me 3/2, and then I've got to divide by 1/2 plus 1, so that's 3/2. But when you divide by 3/2, it's the same as multiplying by 2/3. So you get 2/3 t to the 3/2 for your answer plus a constant. Now, I didn't mention the constant in these other steps, but remember, each step you must add the constant. Okay, so that's the antiderivative of t to the 1/2. Now, this could have been written as square root of t, and then you would have had to write it like this so you could see how to apply the power rule. Okay, so this one over here is not written as a power, but you can write it as a power. The square root of x cubed can actually be written as x to the 3/2. So this integral needs to be rewritten, and then once I rewrite it, I can apply the power rule. So the antiderivative of x to the 3/2 would be x to the 3/2 plus 1 divided by 3/2 plus 1 plus a constant. And then 3/2 plus 1 is 5/2, so that would equal x to the 5/2 divided by 5/2 plus a constant. And then dividing by 5/2 is the same as multiplying by 2/5. So you write that as 2/5 x to the 5/2. And now you can check each one of these by taking the derivative of the answer and making sure you actually get the integrand. But you don't really have to do that if you do the work properly, because you may not have time to check on some assessments. Okay, so here's another one. I have 1 over x to the 3/5. Well, I can write that as the integral of x to the negative 3/5 dx. Well, then I would have, if I apply the power rule, that would be x to the negative 3/5 plus 1 over negative 3/5 plus 1. Well, negative 3/5 plus 1 is 2/5, so I have x to the 2/5 divided by 2/5 plus a constant, and then dividing by 2/5 is the same as multiplying by 5/2. So I'd have 5/2 times x to the 2/5 plus a constant. Now, there are some more rules. I went ahead and gave the zero rule the number 0. So the zero rule basically says that if you integrate 0, you get a constant. Well, that makes sense because what's the derivative of any constant? 0, right? Okay, so now the constant rule says that if you integrate a constant, you're going to get the constant times the variable, in this case x, plus another constant. So this constant, the k, will be a known constant and the c will be an unknown constant. So for example, if you integrate the constant 5 with respect to x, it's actually going to be 5x plus the constant c. Now if you take the derivative of this, you know the derivative of 5x is just 5, so therefore you know that's correct. And then you have the constant multiple rule, which says that if you want to integrate a constant times a function of x dx, then you can actually move the constant outside the integral as a factor and say k times the integral of f to the x dx. Now that comes in handy, and actually you don't have to do this, but you can do this, in other words, you can do this in your head, but let me show you how this works. So if you integrate 5x squared dx, you could actually take the 5 and move it to the left of the operator, and so you have 5 times the integral of x squared dx. And then if you integrate x squared dx, you get x cubed over 3 using the power rule, but then don't forget your constant 5, so you have 5 times x cubed over 3 plus a constant. Now some of you might say, well, wouldn't you have to distribute that 5 through the constant as well? But the deal is that it really doesn't matter because 5 times a constant is still a constant. So we don't have to concern ourselves with what the constant is at this time. And then there's a sum rule and a difference rule. If you want to integrate the sum of two functions with respect to x, then it would be the integral of the first function with respect to x plus the integral of the second function with respect to x. So if you wanted to integrate x squared plus x with respect to x, then you simply integrate the x squared function with respect to x, and then integrate the x function with respect to x and add them together. And you can do those with the power rule, and you get x cubed over 3 plus x squared over 2, and then plus a constant. And again, you only need one constant. Even if you do these separately, you know, you're going to get a constant for this integral and a constant for this integral, but of course if you add the two constants together, you're just going to get a single constant. Same thing with the difference. The integral of the difference of two functions is the difference of the two integrals. So if I had x squared minus x instead of x squared plus x, it would work exactly the same way, except I would subtract. So I'd have the difference of the two functions. And then we already talked about the simple power rule. You can freeze the video here if you want to and read these rules. Every time I've taught business calculus, I've never covered the trigonometric rules, but each of the trigonometric functions have a rule that could be memorized if you needed it. So just a quick example, if you wanted to integrate cosine x dx, it's actually equal to sine x plus a constant. So if you wanted to integrate 2x plus cosine x dx, well, you know how to integrate 2x. It's just going to be x squared. And then you would use this rule to get the integral of cosine x, which would be sine x. And then, of course, you would add a constant. Now, again, you don't really need to pay attention to these examples unless you feel the need to. So here are some basic rules of integration, and you can just read over these. This applies the constant rule. This applies the constant multiple rule, and this one also applies the constant multiple rule. And then this is the sum rule, but I used a trig function, so if you want to, you can skip this one. I'll just go ahead and go over this sum rule. This is the integral of 3 square root of x plus 5 over x cubed dx. Well, that's the same as 3 times x to the 1/2 dx plus 5 times the integral of x to the negative 3 dx. So then you can integrate x to the 1/2 using the power rule, and you get x to the 3/2 over 3/2. And then don't forget you got to multiply that by 3. And then you can integrate x to the -3rd by adding 1 using the power rule. So you get x to the -2 over -2, and then you got to multiply that by 5. Well, 3 divided by 3/2 is 3 times 2/3. So the 3's are going to cancel, and you're just going to get 2x to the 3/2. And then 5 divided by -2 is actually going to give you a -5/2. So you're going to have -5 over 2. And then I moved the x to the -2 to the denominator and made the exponent positive. So I get -5 over 2x squared, and then plus a constant. Now, you can actually skip over the rules. You don't have to write this as two integrals. Just know that the rule allows you to write it as two integrals. And then notice that you can just go ahead and integrate 3x to the 1/2 here, and then you can integrate 5x to the -3 here, and then throw in your constant, and then simplify what those two expressions are. So you don't have to break it up like I did up here using these rules. But the fact that we're allowed to use those rules is what allows us to integrate it without breaking it up. Okay, now here are some other examples I want to go over real quick. Notice on each of these I used algebra to rewrite the integral. So this one I just expanded it, I multiplied it out, and I got this, and now we know how to integrate this term by term. On this one I factored the numerator, and then I was able to cancel the x minus 2's, and then I just integrated the result. On this one I can break it up into two terms, x cubed over x squared minus 3 over x squared, and then that would be x minus 3x to the -2, and then I can integrate it term by term. And then the last one I can factor the top into e to the x minus 1 times e to the x plus 1, and e to the x minus 1 over e to the x minus 1 is 1, so I'm just integrating e to the x plus 1, which you know how to do. The integral of e to the x is e to the x, the integral of 1 is just x, and then don't forget your constant on all of these. There's a couple of practice problems you can look at and try those. The answers are written below them, so you can freeze the video and try those. And then I've got one more example I want to show you. It turns out that if you have additional information regarding a function, you can use that information to find c. Go ahead and read the first example. I want to focus on the second example. Alright, suppose a rock is tossed upward with initial velocity at 64 feet per second, initial height of 100 feet. Find the position function for time and s of t for position, and then find when the rock will hit the ground. Okay, so we know that the second derivative of position is acceleration, and using feet and seconds, we know acceleration of a falling object can be written as -32. So that's what our acceleration function is going to be, -32. Well, if we integrate this, we'll get the first derivative, which would be -32t plus the first constant. Okay? Well, the first derivative represents velocity, and we were told that the velocity at 0 is 64. So if I evaluate this derivative at t equals 0, I get c1 equals 64 is the constant. So now I know the velocity function is -32t plus 64. And now to get the position function, I can integrate this to get s of t. And when you integrate this, you're going to get -16t squared plus 64t plus another constant. But now we know that the position at 0 is equal to 100. So just plug 0 in here, and you'll get c2 is equal to 100. And so now you know c2 is 100. So now you can actually get the second constant, which is 100. Okay, and then from there you can answer the question. The final question says, when does it hit the ground? So just set the position function equal to 0 and solve it using the quadratic formula. And that's the end of this section.